Well, ladies and gentlemen, welcome today to the lecture by Professor Fukaya, the Shaw Prize winner for this year's Shaw Prize. And Professor Fukaya is coming from the Yale Institute, the Mathematical Science Center, and Tsinghua University. And today we are actually very honored to have Professor Yao coming himself to this lecture. So may I ask my colleague from Math Department, Frederick, to introduce our speaker today. I see. So one thing I forgot is that I represent the university and the IAS to welcome you all. Okay, so yeah.
Okay. Good afternoon, Professor Fukaya, Professor Yao, and colleagues, students, and visitors. So it's a great honor to welcome the 2025 Shaw Laureate in Mathematical Science, Professor Fukaya, who is with us today to share his academic journeys and excellence. Okay, so the Shaw Prize Foundation was established in 2002 under Sir Run Shaw, and the first Shaw Prize was presented in 2004. Okay, and it honors individuals who have achieved distinguished and significant advances and made outstanding contributions to academic and scientific discoveries. Okay, and Hong Kong UST take prize to be one of the 3 institutions to host the Shaw Prize lecture every year. So on behalf of Hong Kong UST, I would like to first thank Shaw Foundation for bringing us to this year's Shaw Laureates, okay, to our campus. Okay. So Professor Kenji FUKAYA grew up in Yokohama in Japan, and he received his whole education in Japan, including his PhD in University of Tokyo. And then he began his academic career in University of Tokyo and then moved to Kyoto University as a full professor in 1994. And then in 2013, he became a permanent member for the Simon Center for Geometry and Physics at Stony Brook University in the United States. And recently in 2024, Professor Fukaya moved to China and became a full professor at Beijing Institute of Mathematical Sciences and Applications, BLIMSER, and also Yale Mathematical Sciences Center at Tsinghua University in Beijing, where he is currently holding his position. Okay. So the Shaw Prize this year was awarded to Professor Fukaya for his pioneering contribution to symplectic geometry, especially for the discovery of an algebraic structure, which nowadays called Fukaya category. So it's a category which consists of Lagrangian submanifold in a given symplectic manifold, such as a torus or Calabi-Yau manifold. Is closely related to the Arnold's conjecture, which asks about the lower bound on the number of intersection points between 2 Lagrangians. In 1980s, a German mathematician, Floer, initiated the Lagrangian Floer theory as approach to tackling the Arnold's conjectures. Based on infinite dimensional Morse theory. And he was able to solve some special cases of this conjecture, yet the general case remained difficult partly because the moduli space of solutions to the involved PDE may be highly complicated and singular. Okay. And then in around 1993, Professor Fukaya discovered a higher algebraic structure in such a complicated and singular moduli space and proposed a vision to assign category, which nowadays called the Fukaya category, to any symplectic manifolds. Okay? And then Professor Fukaya, together with his collaborator, Professor Yonggen Oh, Hiroshi Ota, and Kaoru Ono, they have established and also significantly extend the Lagrangian Floer theory and make significant breakthroughs to the Arnold's conjectures. So today we are very honored to have Professor Fukaya, who will be delivering a talk called From Shapes to Space, and share with us his academic discoveries. So let's welcome Professor Fukaya.
Thank you very much for introductions. I want to talk something under the title of shapes. From shapes to spaces. So I can just say that geometry is one of the oldest areas of human knowledge. And all the ancient culture, civilizations developed something about the geometry. And many facts, knowledge are collected by various civilizations. One of the typical example is this Pythagoras theorem. So this is a Chinese classics. I don't know how to read it in Chinese, but it's in Japanese it's called Sankyo. But it is all Chinese classic books, and you can see that this is a proof of Pythagoras theorem. We have this four right rectangles, and this gives a proof. I think you can know it. So now, what is very deep, but what is typical in mathematics books in those days? Most of the mathematics books are written in a style to present the problems and its solutions. This is also the case of this book. This is called a Lind Papyrus. This is came from Egypt. It's not hard to read, but you can see that there are several problems written and some answers are given. And I want to show you another book. This is not such old, but it's a rather old Japanese math books by Takakazu Seki, famous Japanese mathematician in Edo period. And here you see that I think this is a problem, right? And it is written problem here, and the solution this is solution, right? Solution is written here. So this is a style of math books in old days, and this is very similar to this student book for studies. So this is a student book to train entrance exams in Japan, and the style is very similar, right? So you see that this is the problem. So you have this something about the inequality of second degree and blah blah blah. Then this book gives the solutions. Then they put another problems, and I think this is not a solution. This is how to solve it, and then they just give solutions. So this is the way this recent recent study book for high school students is written. So, but then there is some So there is some kind of a paradigm shift, probably in Greek, when people start to describe various knowledge they know on shapes more systematically by axioms and proofs. So in place of presenting individual facts, they are solving individual problems. They start looking for logical relationship among those theorems and to derive many theorems from a small number of axioms. So this is the famous Euclid elements. So they prove several one-to-one. This is another famous, I think this is a book in Alexandria, right? Apollonius. It's about the conics. And you have very similar things that you have the statement and the proofs. And this is another very famous book, Newton, the Principia, in the Renaissance. And Newton is much influenced by this Greek tradition. So he wrote this is corollary 4, and then he gave a proof. And corollary blah, 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 he gave a proof. So that is more modern style of the mathematics. And this is closer if you look this more recent paper in mathematics. So now, let me say something similar. So in popular music, there are album called concept album. And the usual album in popular music just provide various songs individually. But then that is called a concept album, means that this album has a concept. So many songs just form one story, so that in total it gives some story. And I think this is the famous album of Beatles, and which is, several people say that's the first example of concept albums. Another I want to say that this element of Euclid is a concept album in mathematics compared to this high school study books. So they put many statements like theorems into one kind of stories. That's what they do. And then what happens from this thing? So once one make various facts on shapes into one story, then something appears, that's a new concept, that's called spaces. So before Greek time, before this Euclid kind of things appears, they study individual objects like triangles, rectangles, lines, etc. individually. But then once they start systematize those various language, then they will find the notion of spaces. So let me explain this a bit. So this is a famous theorem. I think all you know, all in this room should know these theorems, right? You have theorem about triangles. If you have one triangle and three angles, then you take sum of them, it's pi. So that's famous theorem. And another famous theorem is this Pythagoras theorem, right? When you right triangle, so this is a right angle, and you have these three A, B, C, three lengths, and the C is bigger than A and B. Then you have this famous equality, A square plus B square is equal to C square. And all days, I think, certainly before Euclid, many civilization knows these two theorems kind of individually. But actually, we now know that these two theorems are related each other because they both said that the space is flat. So there's this theorem about three angles in triangles, and this Pythagoras theorem both said that the space we are living is flat. In fact, if you consider the space which is not flat, then the sum of three angles is not pi, but it's strictly smaller than pi. So this is a kind of schematical drawing of triangles in a space of negative curvature. Then that three triangles is equal to this smaller than pi. And if you run about the trigonometry on the space of negative curvature, this formula is actually changed to this a bit more complicated formulas. And I can say more example, which is actually related to what I want to talk later. So it is about the intersection of lines. So in a space, in a flat space, if you have two lines, L1 and L2, then its intersection is usually just 1 point. But in exceptional case, these two lines are parallel, so it means that they don't intersect. But this is really exceptional. It means that if you tilt the second line any small amount, then they start intersecting, right? You have two lines, and you tilt this guy any small amount, then they start intersecting. But this property is very much typical in a flat space. So this is a similar picture in a space with negative curvature. This is actually a straight line in a space of negative curvature. And you have these two straight lines which does not intersect. This is not called parallel, but it's called a superparallel. And if you look this, if you tilt this red one a bit, it still do not intersect. And this happens in the space of negative curvature, and it is very much different from the space of from the flat space. So now, because this Euclid and those people try to prove many theorems like a space of flat. So this fact that after any tilt, two flat parallel lines get intersected is one of the important things written in Euclidean theorems, and they use it to prove many theorems like sum of three angles equal to pi or something. And then once people very hardly try to understand how these theorems are interrelated, they finally found that the concept of spaces, because in the 18th or 19th century, people found that there are different kinds of geometry where spaces, where these lines may not intersect in this way, but intersect in the other way. And that is discovery by this Lobachevsky or Boyai or those people about the non-Euclidean geometry. And I want to emphasize that this discovery of non-Euclidean geometry became possible because people do not individually think about the shapes or theorems, but they study many of them in a very systematic way and study how they are related. So this is an idea of how these geometries are going. And then after this non-Euclidean geometry was discovered, Riemann found the idea of a manifold that's a space of high dimensions. And then this notion of manifold is in a sense dominant in 20th century geometry, so that the space in our century or last century is nothing but a manifold. But then after a while, this notion of manifold is established. People start wondering whether this notion of manifold or this kind of spaces is a final one, or you need any more general ideas of spaces beyond manifold. I want to mention one of Yeah, I want to mention one idea which a bit related but not so completely related to what I'm going to talk. It's an idea of non-commutative geometry. And the idea of the non-commutative geometry is the following. So we have a space X is the space. We consider the set of functions on it. Function just associate f of x to any x of this space X. Then you can multiply two functions. And the very important property of this kind of function is just multiplication is just commutative. So you have something commutative, and so this is the kind of, so that you can replace this space X by so-called a ring of functions, which is a commutative ring. But there are some different kind of multiplications, which is not commutative, and the very typical one is a multiplication of matrix. If you multiply this matrix and this matrix in this order, you get 2, 1, 1, 1, and in the opposite order, it is 1, 1, 1, 2. So you have a multiplications which is not commutative. So now, people start to think about there might be a space so that the ring of functions on this space is not commutative. And that idea probably is inspired by quantum mechanics. In quantum mechanics, there are something called the matrix mechanics, so that this matrix kind of thing is very much important. And to physical quantity, it may not be commutative. And this kind of ideas appeared and maybe significantly developed in functional analysis and theory of operator algebras. And this is a famous book of Alan Kohn, which discusses this kind of non-commutative geometry. And I don't want to talk this kind of non-commutative geometry, but probably what I'm going to talk is related to some non-commutativity in a different way from this people in functional analysis is doing. That's something I call infinity things. Okay, so now this is very much a beginning. And I just want to jump 10 or 20 more years. Then there is some concept which is called mirror symmetry appeared. And mirror symmetry appeared in 1990s. And at the beginning, maybe not so many mathematicians are interested in it, but at some point, mathematicians start very much curious and interested in mirror symmetry. The reason is the following. So I just want to mention very briefly, because something more I will come later. So in mirror symmetry, you have the situation that you have some space, X, and some other space, X check. They are different in a usual sense of manifold. But in mirror symmetry predict that these two different spaces are actually the same. So this is what this mirror symmetry predicts. And and also this kind of equality gives very highly non-trivial equality in mathematics. And that's why mathematicians are so much interested. And for me, the fact that the two spaces, which looks the same in a different in the classical sense, just became the same is very much mysterious. And I was very much interested in it. And if I want to try to understand this concept, probably for this physicist, think that the notion of spaces, the space is a field theory. So I want to say a few words why it is so. In elementary particle physics in the modern days, you cannot directly observe what is happening, because many important things are happening in a very microscopic level. So you can never observe this microscopic level yourself. What you do is that you use a lot of big equipment to do this experiments, and you get some numbers. So this system of numbers are supposed to be something you get from microscopic spaces. And then you have to replace this system of numbers to this microscopic spaces. But of course, for human, just you have a chaotic system of numbers, you don't get anything. So you need to understand you need to see some geometry or some shapes or spaces in the microscopic levels, so that this system of numbers is just the outcome of these microscopic things. And what predicted by this mirror symmetry, or more generally string duality kind of thing, is that even though these microscopic things looks different from the point of view of usual geometry, but the system of numbers you obtain out of it actually coincides. So that is the discovery by physicists at the end of 20th centuries. So that's another hint to mathematicians that we have to go beyond the usual spaces and to somehow redefine the notion of spaces. And I just go back to more kind of mathematical things and how this kind of thing works. So I want to explain something about symplectic geometry, the mathematical areas I was working on. So symplectic geometry is a space, so-called symplectic spaces, and it has a two type of coordinate. P is the positions, and the Q is the positions, and P is the momentum. It's a velocity. So I mean, in our space, we just usually consider where we are. So our situation is just described maybe three variables, Q1, Q2, 3. That's the positions. But what's important in symplectic geometry is that we consider the velocity we are moving in the same footing as the position we are there. So in place of taking three variables in our three words, it is Q. So this is a blackboard. This is just plain, so I have only two coordinates. So this position, Q1 and Q2. So usual sense is that your situation is just described by two positions, Q1 and Q2. But you regard the way that they move, P1 and P2, this vector, in the same footing as the positions. So you have this, in a two-dimensional case, you have these four variables, Q1, Q2, P1, P2. That is the basic idea of symplectic geometry. And not only that, you have this particular expression, W, or omega, dqi, wedge dpi. Maybe I'll explain what this expression means, but this is something called a symplectic form. And so you consider this two n-dimensional spaces together with the symplectic form as an object. And the origin is the following. So origin of symplectic geometry is an equation of motion by Newtons. So equation of motion by Newton just means that you have a second derivative of the positions you are moving. It is proportional to the forces applied to these particles. And the fact I think this is second derivative is very important. I think it takes, in Greek time, probably Aristotle do not know, and I think he misunderstands that his first derivative is determined by something. And I think it is Galileo Galilei, so that the actual force kind of affect the motion through accelerations, that's second derivatives. So Newton formulated this notion of second, these equations. But then we can modify these equations in a bit different way, and that's due to Hamilton. An important case is that energy is preserved. So like in a case, if we are moving in Earth, then there is something called a potential energy. It means that if you go up to the hill, then you have to work hard, then you get some energy. So in a high place, you have more energy compared to the case when you have in a lower case. And this W is an energy. And this means that so you have in a high place, then you have a very big slope. Then the force is to the direction that this height is decreasing. So this is W is called a potential. And then you can realize, then you take this function h. This is the square of the 1/2 of the sum of the square of the velocity plus this potential energy. So this 1/2 of the square of velocity is the energy you get by moving. So once you move fast, you have energy. And at the same time, if you are in higher positions, you get W. And you take this sum. And what Hamilton found is that you take this particular sum, then this Newton's equation is just the equivalent to these very simple equations. So that if you just take derivative of Q, it's P. So Q is a position, P is derivative. So if you take the derivative of Q, you get P. But then you take derivative of P, so it is the second derivative of Q is force. And the force is this minus of the derivative of W. So this is a very particular equation, so-called Hamilton equations. And Hamilton changes this Newton equation into this form. And what is very typical to this equation is that conservation of the energy. So it is written in this way. If your motion is controlled by this Hamilton's equations, then you take this energy you have at time t, its derivative of t is 0. It means that energy is preserved. And this kind of thing is very much typical in an astronomical phenomenon. In a world of astronomy, so the moon or Earth just moves in a vacuum, so nothing kind of, you don't lose your energy. In Earth, you just do this like this, and then it stops at some point because it is not in a vacancy. But so you want to have a model of the astronomical phenomenon. This Hamilton equation is very nice. But then, so this is the discovery of Hamilton's. You can use this energy preserving to write your equation in this particular form. And this is actually very useful for a long time. And this is the origin of one origin simplex geometry. But simplex geometry has one need another discovery. It is the following. So I wrote this omega here. So omega, so you have these two things. And this is something like two small, very small particles. And for the role of omega is that you have given omega, then if you have some two-dimensional object, surface in your symplectic spaces, you get an area. So you can summarize this, the symplectic space is something so that the area of the surface is always defined. So that's what simplex geometry means. So any symplectic space and any surface, you have its areas. And why it is important? So you consider these things. So suppose at time 0, you are on this sigma 0. Sigma 0 is this two-dimensional object, the surface. Then you start from here and you move according to these equations. And suppose you are time t on a surface sigma t, another surface. So this Hamilton's equations induce some motion of two-dimensional objects. And what's very important in this is that you take this area of this sigma t with respect to this symplectic form, then this is a constant. So it's not only this energy, but also area of surface is preserved by this symplectic form, by these Hamilton equations. So Hamilton equations preserves area of two-dimensional object. So that's very fundamental things. That's why this omega symplectic form is very much a kind of central object in symplectic geometry. So that is what this Hamiltonian dynamics means, and that's how this symplectic geometry started. And I want to say a few other important things which I'm interested in, and also it's a main subject in symplectic geometry. It's called the Lagrangian submanifold. There are many kinds of Lagrangian submanifold, but most typical Lagrangian submanifold is something I wrote LC. So suppose you have, so let me recall that symplectic spaces, you have a position and the momenta, position and the velocity. And you take some C1, Cn, some constant, and you consider the set of all points on the symplectic space so that the position Q1 to Qn is given by this C1 to Cn. But you do not require anything about the velocity or positions. So it means that at this moment you know that you are here, but you don't know how fast you are moving. If you consider this particular situations, it is a very important part of the important example of Lagrangian submanifold. So in Lagrangian submanifold, for example, you know the positions, but you don't know the velocity. And it is also similar that if you know the velocity, but you don't know the positions, then you are also given Lagrangian submanifold. So this is the half of the dimension of fold freedom. And this notion of Lagrangian submanifold is actually very much basic in symplectic geometry. And I feel that maybe at the beginning of quantum mechanics, and also this uncertainty principle, knows that if you know at these positions, then it is impossible to know how fast you are moving, right? This is the Heisenberg principle. So this kind of thing is very consistent with this quantum mechanics. Actually, symplectic geometry plays some important role, or at least Hamiltonian formalism plays very important role at the beginning of quantum mechanics. So I think that's somehow related. So the Lagrangian submanifold is this kind of manifold. So now I want to explain for how this kind of thing is used. So let me consider one particular problem in Hamilton dynamics or mechanics. This is the following problem. Suppose that you know that a particle is at position 0. I'm sorry, I forgot to write it, at time 0. Suppose that this particle at time 0 is in position 0. So it means that here. So this line, L0, is just the position that your particle is situated at the beginning. And suppose you know that at a time t, the same particle is at position C. So here this LC, so that your particle at time t is exactly on this so you have two Lagrangian submanifolds, L0 and LC, so that you know that at time 0 you are on L0, at time t you are on LC. And the typical and important problem of mechanics is that once we know these two conditions, you want to know how the particle moves from the time 0 to time t. Then how to solve it? So now we consider this Lagrangian submanifold time 0. Then you let this move following this Hamiltonian dynamics. So if you are here, then you move here, blah, 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 and then you move this whole line, then you end up with some other line. So let this line to be LT. So this line is moving as time going, and then you finally became this LT. And what's important is that by this time shift by this Hamiltonian dynamics, the Lagrangian submanifold remained to be a Lagrangian submanifold. So at the beginning, it is very simple Lagrangian submanifold, but at the end of the day, it may be this kind of a bit more complicated, curved Lagrangian submanifold. So what you know is that you are in time 0 here, you are time c here, t here, but also due to the fact you are on this line at time 0, you know that at time t you are on this curved lines. So it means that by these two assumptions, you know that you are one of these three intersection points, right? Let me repeat. So first you know that you are on this line at time 0, and you are on this line at time t. But then you move this line by this flow, and you get this LT. So it means that in time t, you are both on this line and on this line. So you should be at one of these three intersection points I draw green. So this typical problem of mechanics, it just reduces the problem how two Lagrangian submanifolds intersect. That's somehow similar kind of problem that I just discussed for this, how these lines are intersect. So how this Lagrangian submanifold intersect is in a sense very much a central problem in symplectic geometry. So I will go back to that problem later, but let me state one version of the mirror symmetry at this stage. This is a particular version Maxim Kontsevich proposed in 1994, which is called the homological mirror symmetry. And I want to make it a bit more precise, so this is stage 1. So homological mirror symmetry at stage 1 is the following things. Mirror symmetry gives a pair of spaces, X and X check. As I mentioned before, it is very important that X and X check is different. But what is true is that X as a symplectic space is the same X check as a complex space. So this is the mystery of mirror symmetry, because you have two different spaces which looks very different from just naive or classical sense. But if we regard X as a symplectic space that is with symplectic form, and another thing as a complex space, I'll soon go back there, but maybe it's a bit easier than symplectic space for you. You have some complex numbers. Then the claim is that X as a symplectic space is equal to X check as a complex space. But this is not a good statement from a mathematical point of view. But mathematicians should say that, okay, what do you mean by symplectic space is equal to complex space, right? Because this is just in mathematics, it is nonsense. So you want to make sense of this. And as I said at the beginning, the way we understand spaces is we put many shapes on the spaces, and we observe that how these shapes behave in the spaces. And you see the way how shapes behave in spaces, then you understand the space itself. Because you know that here, you can see a lot of objects like this by yourself, and there are many objects, but spaces behind it you can never see directly. So the space you can see only through the object which is contained in the spaces. So now let me try to do that one here. So then I want to make it a bit precise. As I say that Lagrangian submanifold and its intersection is very important in symplectic geometry. So that we claim that mirror symmetry is that the way that Lagrangian subspace submanifold X intersect is the same as the complex subspace intersect in X check. So this is a bit more mathematical. So in place of saying that X as a symplectic space is equal to X check as a complex space, we say that the Lagrangian submanifold X and how it intersects in X looks the same how the complex subspace intersects in X check. So this is the second stage. So I want to make it a bit more precise. So let me recall what is the intersection in a complex space. So what is a complex space? So it's a bit easier, right? You have complex space is locally c to the power n. It's just the n tuple of complex numbers. So g1 to gn are complex numbers. N tuple of complex numbers are complex spaces. So what is a complex subspace? A typical way to obtain complex subspaces is through equations of this kind. So this is a polynomial. So I1 blah 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 I is just complex numbers, and this is the integers, non-negative integers, and this is a finite sum. You have this polynomial, and it takes a zero of polynomials. That's a complex spaces. So this is the complex space and the complex subspace. Oh, so what do I mean? Then what is the intersection of complex subspaces? So we consider a very simple case that two-dimensional complex subspace is coordinate W and Z. Then you consider two kinds of complex space. One is this W is 0. And the other is W is P of Z, and P is the polynomials. So you consider intersection of this A and B. And intersection, of course, is given by the equation P is 0. Right? So this is the usual polynomial equations. So now let me recall the famous theorem. I think that's first stated and proved by Gauss. The number of solutions of this algebraic equation, 0 equal to pz, counted with multiplicity, is exactly equal to the degree of polynomial p. So this is the famous theorem, probably maybe beginning of university level. But it's very non-trivial and interesting theorems. So let me elaborate this theorem a bit. So we consider this particular case of this degree 3 polynomials, g cubed plus d squared plus z plus 1. And you can solve these equations easily. Minus 1, square root minus 1, and minus square root minus 1. 3 solutions. It's this degree 3. And the other case is g cubed, 2 of g squared plus g. And this is, I think, minus 0 and minus 1, right? I mean, you divide by g squared plus 2z plus z is z plus 1 squared. So 0 and minus 1 are solutions. But this is degree 3, but it is two equations. And you know that the minus 1 is something called multiple solutions. And you count with multiple solutions, the number of solutions is always 3. Okay. But then I want to go to real geometry. So complex geometry, in the world of complex geometry, number of intersections, in a sense, kind of does not change when you deform the spaces. You just count multiplicity. But in a real geometry, simplex geometry belongs to real geometry, so the situation gets very much different. So you consider the same equation, g cubed plus g squared plus z plus 1 is 0. But in this case, you consider only real solutions. They have just exactly one answer, minus 1. And then you have another thing, z squared minus z is 0. You have 3 answers, right? 0 and plus minus 1. So the degree and the number of real solutions is more chaotic. It's hard to understand the relations. And the reason that this solution is changing is you can explain the following way. So you consider this particular equations. It has 3 equations. And you start deforming these equations, z cubed minus z plus epsilon, by just changing, putting epsilon, which is a positive number. Then you draw the picture like this. So this is at time 0. You have this graph, and you have another graph. It intersects at 3 points. Then you move a bit. So at the beginning, you have this black one, 3 solutions. But then you move this, and at this red line, you will see there's multiple solutions here. Then after you pass multiple solutions, you have this green line. Then it has only 1 intersection. So the number of solutions changes as the time going, as you deform it. And this is very typical in real geometry, and it is very different from complex geometry. And so what we obtain from this? In a real geometry, intersection come with sign. Sign is a kind of, each intersection you can assign plus or minus. If you look at these pictures, you have these 3 intersections, and this guy go from negative to positive. This guy goes from positive to negative. This guy from negative to positive. So you put plus sign to those intersections which goes from negative to positive. And you take minus sign which goes from positive to negative. So you count these 3 with sign, then 1 minus 1 and 1, it is 1. And then this 1 does not change. And also you can say that there is a cancellations of intersections between positive sign and negative sign. So you see that this picture. So you have 1 intersection with negative sign and 1 intersection with positive sign. And at this moment, they disappear at the same time. So 2 intersections cancel each other. So this sign and the cancellation is very much typical phenomenon which appears in real geometry and does not appear in complex geometry. So now, this is kind of more naive, but then if you want to make more mathematical and more systematic, we have to kind of study this phenomenon a bit more precisely. So in algebraic geometry, people use something called a tensor product. And so algebraic geometry is very much important part of complex geometry. So in algebraic geometry or complex geometry, people introduce some notion of tensor product to understand these intersections. And I'm sorry, I cannot define this notion of tensor product, but you have this ring of two polynomial 2 variables, and you just put these equations. This is so-called a module over this ring, and you have another module over this ring, and you take tensor product over this ring. Then this tensor product has rank 1, it's just a C. And this fact reflects the fact that these equations, W minus Z, W equals Z, and W has just 1 intersection point with multiplicity 1. And then, if you go to the next cases, if you consider this equation, W is Z squared, so you have another module, and you have another module, W is 0, then this tensor product, if you define it properly, it's C squared, it's rank 2. And this reflects the fact that this intersection has a multiplicity 2. So I don't explain very precisely, but this geometric facts, you can reference using more algebra of tensor product to understand this multiplicity. But I think I want to go further. So this is the picture I just draw in 2 dimensions. If you go higher dimensions or more globally, the intersection of algebraic sets behave in a more complicated way. So let me explain another very simple example. We consider S2, that's called a Riemann sphere. It is just a complex plane plus point at infinity. And this is a famous picture called stereographic projections. So this S2 minus this infinity corresponds 1-to-1 to complex plane. So you just so-called compactify complex plane, you get this S2. So you have this S2. Then you consider this curve C in a product of S2 cross C. So this is a complex plane, and this is S2 as I just explained. And in this product, we consider the subset so that W is 0. So this part is 0. I'm sorry, so this is 2 dimensions, but I think I cannot draw 4-dimensional pictures. So just to imitate this 4-dimensional picture by this 2-dimensional one. So this is S2 and this is C, and you have this red circle. This is not actually a circle, but it's a sphere. So you have just one sphere, SC, contained in this S2 cross C. Okay. So now we consider this C, the 2-dimensional subspace on 4-dimensional spaces, and we consider intersection of the C with itself. And of course, this intersection is C itself. So C is S2, and so this is very trivial. But you see that this intersection has a long dimension. It means that if you take the sum of this dimension plus this dimension and the sum, you take difference from the dimension of everything. So 1 plus 1 minus 2, this is 0. And it means that this intersection should be 0-dimensional, but it is 1-dimensional. And this is called a long-dimensional intersections. You can compare to this to a bit more better situation. So this is a formula we expect usually. If C and D is contained in space X, then the dimension of the intersection is given by dimension of C plus dimension of D minus dimension of X. A typical example is this. You have so you have 2-dimensional object plane and 1-dimensional object curve. If you intersect in these 3-dimensional spaces, you get 2 plus 1 minus 3, 0. And you have 3 points. That is exactly 0-dimensional things. So in a nice case, the dimension of intersection should obey this rule. But unfortunately, this is a bad intersection that C cap C is C, and this formula is wrong because this one is supposed to be 0-dimensional, but C has 1 dimension. So this phenomenon is called excess intersections. So the intersection has a long dimensions. And to understand this phenomenon of excess intersections is another very important point of intersection theory in complex geometry. And and I can mention some other things. In this particular case of the C, so you can just move C to C epsilon so that we require W to be epsilon. You can just parallelly move it. Then C and C epsilon get empty, right? So you have 2 complex objects so that you move a bit and it gets empty. This is very different from usual complex geometry. So you consider the case of this W is 0 and the W is Z, then you move it, you still intersects. But this became empty is somewhat different. But then then we need something called a derived version of the intersection theory, which I am unable to explain. But it means that there is some series of so-called invariant called the torsions. I think this is start K from 0. So you have this tau K, mm prime, and the 0 one is just a tensor product. So you just generalize tensor product using tau to get some kind of a derived analog of intersection point in theory. And in this particular case of this C, on this S2 in S2 cross C, this tau is always 0. It corresponds to the fact that you perturb C a bit, they don't intersect. So this is something called a derived intersections. And actually the number is just given some dimension of the tau, but counting with plus minus sign, depending on the parity of the K. So this is a kind of typical things about intersection theory in complex and algebraic geometry. But then I want to talk more. So what I mean is that tau is actually a very much important notion in homological algebra. And as I said, that the homological means symmetry, and this homological means that this one of these kind of things. But I want to go more on the symplectic geometry. And in the symplectic geometry, it's a real geometry. But in this case, intersection theory is a bit more different. And that is due to Andreas Floer. There is some another kind of intersection theory called Floer homology. So let me go back to this intersection in a real geometry. So you have these 2 arcs. This is actually a Lagrangian submanifold in C. And you say, as I said, that there is cancellations in these cases. And the cancellation means that you have these 3 intersection points. But this is plus, minus, plus, and these 2 you can cancel, or these 2 you can cancel. But these cancellations, actually in Floer theory, became more systematic, and you can say that the cancellation of the numbers, you can kind of upgrade it to something called a boundary operator, so that the plus or minus sign becomes some kind of degree of Floer homology, and that's how this Floer homology is started. So I want to explain how it works. So in this case, we consider this line, and we consider this another line, and you take this domain, you have this two-dimensional object, which somehow interpolate these two intersections. And the idea of the Floer homology is just by just counting this kind of two-dimensional object, you see how these points are cancelled. So that's the basic idea of the Floer homology. So it is the following. So you see that this line, that this pink one gives, this purple one gives some operation so that P1 is moved to Q1, or mapped to Q. P1 is mapped to Q, and this pink one also is a map that P2 is mapped to Q. So this map, and then it gives this kind of thing. So this P1 and P2 has a positive intersection. That's actually degree 0. And this Q has a negative, negative intersection. That gives degree 1. And then you have this pink one and blue one, which gives some map from here to here. And this, this cancellation just is reflected to the linear map between this two-dimensional vector space and one-dimensional vector space. And then what we really found is something called a Floer homology. And after this cancellation, Floer homology of these two ones is calculated. These two are cancelled. So you have this one-dimensional Floer theory at degree 0 and zero-dimensional Floer theory at degree 1. And so this is an idea of Floer homology, so that the cancellation of intersections is more kind of sophisticated, so that you have a boundary map, and the number is just enhanced to have some series of vector spaces. So I wanted, and I just want to say that this is very two-dimensional cases, but in a higher dimensional case, you still calculate some two-dimensional object. And what is the important discovery of Gromov is that symplectic geometry is a two-dimensional geometry, so that two-dimensional object surface has an area. And you just think very naively, of course, then the two-dimensional object play a very key role in it. That's very, this looks very easy fact, but people never realize this really seriously several hundred years after Hamilton. And even after this, Mr. Gromov found this two-dimensional object plays very key role understanding global symplectic geometry. And Floer came just after that to use this Floer theory for the intersections. So let me explain one more example, which is typical in a Floer theory. So we consider this S2. In this case, S2 is a symplectic space. And you consider this equator, S1, as a Lagrangian subspace. Now, what I want to do is just to tilt this S1 a bit, so you have this L epsilon. In S2, you have this equator and a bit tilted equator, L epsilon. And you want to consider these intersections of this L and L epsilon. And naive intersection is, of course, this P and Q, right? This L and L epsilon just intersects at 2 points. But then you look this similar two-dimensional object between this L and L epsilon. You have again this purple one and the pink one. The difference is that before you have the 3 intersections, and the purple one and the pink one is just between different points. But here you have just 2 points, but you have this two strip connecting P and Q. Okay, so now you just draw the similar picture. Degree 0, you have this one P, it's C. And degree 1, we have one C and Q. And you have this pink one, and you have this purple one. And so you just, so it is non-trivial, but you just see a bit more precisely. You will find out that the effect of these two disks actually just cancels, and you don't have any boundary operator. This cancels. Whether it cancels or it gets 2 is very non-trivial. But I cannot explain that, but if you just study mathematics seriously, you will find that this 2 cancels to get 0. So what happens is that you have this 2, C and 0. So you have Floer homology in this case is C in degree 0 and C in degree 1. So that Floer homology of equator and its tilted versions. Okay, and Floer homology is independent on tilt. So Floer homology of L and L is the same. And I want to remind you that this is very interesting because you just forgot simplex geometry and just consider real geometry. Then you can move this L a bit to the north direction to get L epsilon prime, right? Very easy, just move to north. Then they don't intersect. So just in the intersection theory in real geometry, L and L prime epsilon is empty. But this deformation of L to L epsilon is not allowed in a symplectic world. The reason is that in symplectic world, area of two-dimensional object should be preserved. So you look this equator, then you take yellow hemisphere, the northern hemisphere, and you compare this to this L prime epsilon and this part. So this is strictly smaller than northern hemisphere. The area of yellow one and the area of green one is not the same. So if you move this equator to the north, this doesn't preserve areas. So in a world of symplectic geometry, where you have this two form omega, this move actually is not allowed. So it means that in a symplectic world, intersection looks like this, and in real world, intersection looks like this. So that the object in symplectic world intersect more than object in a real geometry. This is called the symplectic rigidity, and this kind of symplectic rigidity is a kind of subject of modern symplectic geometry, and it's very important areas in this 20 or 30 years, and I'm working on it. So now maybe time is going. I have 5 more minutes, right? Yeah. And so I want to talk about. Yeah. So I want to explain the second stage of homological mirror symmetry. It's the following. Mirror symmetry gives a pair with a property that the Lagrangian submanifold of X has a mirror of a complex subspace of CL in X check, so that Floer homology of L and L prime is equal to this torsion of O of CL and O of CL prime. Actually, this is cheating because actually precise statement is not torsion but extensions, and not complex subspace, but it's an object of derived category of coherent sheaf, but I don't want to explain them. So this is not so bad, but not so bad approximation. So this is a rather nice, precise description of homological mirror symmetry, where any Lagrangian submanifold you have a complex object, so that Floer homology I just explained is equal to distortions. This is very similar to what is Kontsevich conjectured. But then I want to go further. And so here we can just take this Lagrangian submanifold and just intersections. But we want to make it even more systematic. Because you want to approximate space by shapes, you need a bit, much more systematic way to describe spaces, shapes. That's where this category is coming. So category is a rather modern notion going to McLean and Eilenberg, but in philosophy, I think Aristotle and those people introduced, but it's somewhat different. So what category is? Category has some objects, and two objects, there is a morphism. So it's very similar, as a simple saying is that C is set, the object is set, and F is a map. We have a morphism. So that's a category. And then the important point is that you have two maps from C to C prime to C2 prime. You can compose two maps. So that is basically what category says. And one important thing is that the composition in category should be associative. You have this 4 objects, you have F here, G here, H here. You first compose G and H and compose F. You first compose F and G and compose H. Of course, this is equal. So this is the associativity. So category is something like you have object and maps between them, and you can compose maps, and the composition is associative. And there are many examples in mathematics. And as I said, that the category is somewhat similar to ring. Actually, in an important case, the set of morphism is a group, so you can add two morphisms, and you can compose. It's something like a multiplications, and the multiplication is associative. So this is something like a ring. But it is not commutative, because this equality FG and GF does not hold, because you can compose this way, but you cannot compose from G to F, right? Because this is a map C prime to C2 prime, and this is map F to C prime, so you can never compose. So you can never, this equality does not even does not make sense. So category is something like a ring, and it's non-commutative. And this is the way this non-commutative geometry appears, but it's a bit different from the people in functional analysis and operator algebra are doing. So now I want to define this category, something called the Fukaya category. I'm cheating, but you have symplectic spaces. Your object is a Lagrangian submanifold. Okay, so the morphism from two symplectic manifold is a Floer homology. It's basically count disks, right? You have these two Lagrangian submanifold. Its morphism is just how this disks looks like. So you have this space, and so you have an object and a morphism. It gives away which kind of shapes it is and how it is related through intersections. But then category theory says more, right? So you can compose morphisms. So you have this composition of the morphisms. So you have this F. So you have these three Lagrangians, and suppose you have this L1. So you have L2 and L3. This is the F. Its intersection point is just some kind of morphism. It's a Floer homology. And from L2 to L3 to L1, you have another G. That is another morphisms. And you can compose it. And the composition, to define compositions, you count the triangle so that this two has these three vertices. And this is the composition of the morphism. And that is basically the category. So you have an object which is a Lagrangian submanifold, and you have two objects. Its intersection gives a morphism. And you have two morphisms. You can count triangle. You can compose morphisms. But actually, the story does not stop here. You can call triangle, but then you can just generalize to this rectangle, 5-gon, and blah blah blah. So you have arbitrarily many gons, which just kind of relate to these intersections of Lagrangians. And this totality gives something called IAS. So what this rectangle is doing, so you have this FGH. Then this rectangle is somehow related that these compositions are associative. GH. I cannot explain why this is related to this, but I can just say that this counting rectangle is very much related to this associativity law of this multiplications. Then, if you consider 5 gons, you have this FGHK, then you start from this 4 morphisms, and you can just 1, 2, 3, 4 different ways to remove parentheses. Right? You have this so you have this first F and G, and that next H and K, then finally compose once more. Then you apply associativity once you get these compositions. Another here you get this here you get another composition, another. So you have the four different kinds of removing parentheses, and you know that in high school you learn that they give the same thing, but it's non-trivial. And how this way of removing parentheses related to this 5-gon, that's the idea of this. And then you can go further, and that gives something called the higher structures, and infinity. So infinity is higher. So you go to arbitrarily many gons to get this higher analog of infinity structures. And what we have proved with Yongin-O, Hiroshi Oda, and Ono is that for a symplectic manifold, we can associate this kind of higher analog of the category, which is called the infinity category, which somehow packed together the information of Lagrangian submanifold, how it intersects, and higher, how this GOM of high many vertices exist. And now, and what this infinity category is regarded as some kind of non-commutative space, and maybe the first approximation of the field theory to which X is associated. This is probably first approximation. Maybe field theory should contain much more information. But this is already somehow much richer than just have a set of Lagrangians or just a Floer homology. You have a big rich structures. So, you just know, you just consider planes, that you consider many lines, and how lines intersect. That's the kind of approximation of the flat plane. In a similar sense that you know which kind of Lagrangian you have and how they interact. That's an approximation of this field theory or string theory. And then the version which I think is very much concerned with what conservative really conjecture is that if you have any symplectic manifold, then you consider this category, infinity category, then you consider mirror, it's a complex manifold. There is something called the category of coherence sheaves, which I cannot explain, but then they are isomorphic. So that's a conjecture. That is 1994. And I think in these 30 years, many progress, not yet completely solved, but now it gets more realistic. Okay, I stop here. Thank you very much.
And we are now in a Q&A section. So are there any questions from the audience or comments?
Well, thank you very much for this wonderful talk. I am not a mathematician, so maybe I start with a very naive question. So from physics point of view, when we have a mirror symmetry, we used to refer to in the physical real space with a mirror plane that can do a reflection. So in mathematics, when you have a mirror symmetry, what exactly do you mean by that?
I think it's something like a symplectic homomorphism, right? So what means that you have x and x check. Some isomorphism of x reflects some isomorphism of x check. But this is not only the story, because there are some isomorphism of this category, or either this Lagrangian thing or coherence sheaves, some isomorphism of the category which does not come from the geometric isomorphism of the spaces. So it means that the symmetry of this so-called field theory is bigger than the symmetry of the space itself. So some of such a isomorphism, some geometric isomorphism, of course, gives the isomorphism of the category. But not all the isomorphism of the category correspond to some geometric isomorphism. It means that you have some geometric isomorphism in one side, you go to the other side, it may not be actually a geometric isomorphism, but some mysterious isomorphism of the category. That happens in many cases, several cases.
I see. So because you are referring to a Hamiltonian with position, momentum, which we usually use the same language in physics, and so by your mirror symmetry, you do not mean that the particles existing in the dynamics, they do not have some kind, they're not constrained by certain kind of mirror symmetry in real space, but some kind more abstract.
I mean, so particle, usually I think means a point, right?
Yeah.
So I mean, my point means a phase space in the symplectic space. But what's interesting is that in the complex geometry, point is a complex subspace. In symplectic geometry, point is not a Lagrangian subspace. Only Lagrangian subspace is half dimensions. But this might be related to this uncertainty principle. So you got a particle corresponding particle is a bit imprecise because the particle in symplectic world should be something like a Lagrangian submanifold. So the fact that you know that you are on this on some positions probably correspond in complex geometry. You are in some complex submanifold. So point correspond. So this is non-commutative geometry. The notion of point it should be something you have to throw away. In symplectic world, the point has less meaning. Only Lagrangian is a bit better meaning.
Okay, thank you.
Any other questions or comments? Yes.
Okay. During the talk, I find that you defined the intersection of C and D. Okay, that one, and you use from the picture. And for the curves intersect. We need to have the two manifolds or two curves to be transversal.
Yes.
And if they are not transversal, how to count the intersection?
Transversal.
If they are not transversal, or if they are overlapping, like sometimes it's 1 point, sometimes it's one-dimensional.
So in the complex geometry.
In the complex geometry.
Yeah, in complex geometry, there is something like a derived intersection theory, and it's established technology. It's not easy. It's several hundreds of pages of books.
In the higher dimension, that's how it's not easy.
But there is there's very established notions of this higher tool to define this Folk homology, derived intersection theory.
No, another question. Okay, I mean, further, a little bit further. How is that intersection with the Zariski and McPherson intersection theory? That's the McPherson and his student Zariski has also as a topological, it's not algebraic. Okay, they talk about singular space with the intersection. Okay,
I think in a complex, if it's algebraic geometry, this Zariski-McPherson type thing is a bit related to this intersection theory, and usually the historical thing is more on regular things, and you go to the space that ambient x check with itself is singular. The intersection theory is even harder, and this intersection homology is somehow related to go that directions.
All right.
Can I ask a question? So, I'm an algebraic geometer, so I ask a slightly technical but question that so in this formulation of mirror symmetry, so we know that in the algebraic geometry for the home space, home AB is usually not the same as home BA, but there's something called cellular duality so it's kind of connected. But is there some duality or this type of phenomenon in this?
Yes. In a Lagrangian Floer theory, Floer homology of L and L prime is always dual to Floer homology of L prime and L. This looks very curious from algebraic geometry's point of view, but this means that if the mirror, in a situation that this original symplectic manifold is not Calabi-Yau, that means that C1 is non-zero. The mirror is not a space, but it has some more extra data, like which is called random gizmo potentials. So in a symplectic side, always it's cell duality holds.
Oh, I see. So it's
in a compact case, actually. What's important is that you non-compact symplectic manifold. Then there is a case that HF L prime is not HF L prime L. So it means that something which is compact in complex side may not be non-compact in symplectic side.
I see. Okay, thank you.
Professor Fukaya, you mentioned that the composition law is non-commutative. Are there any subcategories that are commutative or conditions that force?
I think, the typical thing with commutative is just something called a line bundle, one-dimensional things. I mean, because the matrix is something like a vector bundle, and the line bundle is commutative. And we can just try to see something in a symplectic side that is similar. And another possibility is just you consider something called a diagonal. And in this case, there are very strange cancellations so that Floer homology became commutative.
So, hello, Professor Fukaya. So, I want to ask about some the mirror symmetry pair of things. So, you've talked about something like the Lagrangian subspace in X and and complex subspace in X wedge intersect, right? So, may I ask, is there some pair of duality between these two subspaces, or do there exist some natural isomorphism between those two subspaces, or I mean Lagrangian subspaces and complex subspaces? Thank you.
So I mean that they are kind of different kinds of objects. So X and X check with isomorphic itself does not so much make sense. And what mirror symmetry predict? That you have a symplectic manifold, you have a particular way to cook up category, and for an X check you have another particular way to cook up category, and the category is isomorphic. But the original space itself, in a usual sense, you cannot say that they are isomorphic, because it doesn't make sense in mathematics. Symplectic manifold is isomorphic to complex manifold.
Any other question? Oh.
So I work in high energy theoretical physics, and I'm completely new to all this stuff. So I'm just wondering, so it seems like the intersections tell us how the system evolved from a position to another position classically, and what are the what are the momentum of these particles they can have if they want to go from this point to another point. So is this Fukaya category some kind of classical scattering amplitude thing in field theory. So is that why you call it an approximation for field theory?
Yeah. So, I mean, so you have these two intersections.
Yeah.
As you say that it's something like two objects interact. But then there is something called a tunneling amplitude, I think, in the physics language. So that this kind of effect is just somehow killed. This is what this boundary operator means. And also for this count of triangle, I think in physics language they say it's a kind of 3-point function or blah, blah, blah. And in a most classical sense, if the triangle, only the triangle with area 0 counts. Because in a classical sense field theory, the interaction occurs at some particular point. But this is something like this triangle is something global. So this is some kind of physics which is still very difficult to work out. There is some global interactions, some non-local interactions, and so that is expected to this higher GOND and even higher genus things. So that's a kind of flavor of interactions of particles, which happen not locally but kind of non-local things.
Okay, so can I understand your ways of studying spaces with putting shifts into the spaces, similar to our studying the field theory by sending particles into the potential?
Yeah. That should be very similar, because this kind of thing has a lot of imagination, get a lot of imagination from physics. But I think in string theory, people start thinking about just this kind of global effect, right, by strings. So that's I think, particular relation to this one.
Thank you very much.
Any other questions from the audience? Then maybe I ask my last question. So what is the current status of the Arnold's conjecture, and what are the remaining cases, and what are the difficulties?
So Arnold's conjecture is this study of periodical orbit, and some version of Floer homology is useful. Floer gave some important work, and because there are several other people. And some people study generalizing Floer's work to prove some so-called semi-positive case. And in 1996, Ono and myself and Tiang and Luan and the collaborators and Ziebert gave this so-called virtual fundamental chain. And it proves Arnold conjecture in some particular case over rational numbers with transversal. And so that case is okay. And then but it is over Q. And after maybe rather recently, 5 or 6 years ago, after Blooming and Xu and Shun and those people generalized this story to the case of torsion coefficients. So as far as homology versions, many things are already known, but there are still some degenerate cases, and that kind of thing is still open. So. Okay.
Sorry, I have one more question. So, is it possible to incorporate quantum structures on phase space?
What's quantum structure?
So some quantum structure to this problem. Like if we consider quantum mechanics rather than classical mechanics.
So non-commutative geometry begins with kind of trying to do this kind of things. And I mean, you can just consider the function spaces so that P and Q does not commute. And that I think is what this functional analysis people are doing. And this one is somewhat different. And this quantum mechanics kind of thing is just more local, right? Kind of local geometry. But this one just looks only something very much global. So I don't know how to match them. And so there are some relation, some flavor, but to do rigorously is a bit different things. And if you just say that the relation to quantum mechanics, this guy kind of is something called topological field theory, so that locally nothing happens. So we just look at these global things. And from the point of view of mathematics of symplectic geometries, this topological version is most interesting. But of course, in physics, there are some other things. That's not so much explored by mathematicians, because to include both local and global things is somehow too much difficult.
Okay. Okay, so I think we have a very good time with Professor Fukaya. So let's thank Professor Fukaya again, and thank you for coming.